Okay, so there's a function, same form as functions we've seen. Okay, 0 is the numerator. Five, 6, and -4. Zero is the denominator, or at x equals -6 and 4. So you automatically draw yourself an x-axis. You mark -6, and you put a dotted vertical line there because it's a 0 of the denominator. So when x gets close to -6, the denominator gets tiny. And the closer x gets to -6, the tinier it gets. And there's no limit to how tiny it gets. When you divide a tiny into something that ain't tiny, you get something big, right? So that gives you a vertical asymptote. Now that's a basic principle that people don't seem to totally be grasping. I mean, some people are. And some people say, well, it's a vertical asymptote. I'm not sure I understand why, but that's what you said, so it must be. Okay? Vertical asymptotes. Oh man, this isn't showing up at all, is it? Okay. Maybe just the lighting, but. You really have to understand that, okay? Because if you do, then it becomes obvious that you have a vertical asymptote here. Because your denominator gets tiny, your y value gets huge, okay? Maybe positive, maybe negative. We're going to work out the signs in a minute, okay? So that's -6 and 4. That'll be another vertical asymptote for the same reason. Now, zeros in the numerator make the whole thing 0, right? So I'll get 0 spelled right here in a minute. Zero is the numerator and denominator. Numerator 0, denominator not 0 implies that y is 0 because the numerator is 0. It doesn't matter what you divide by as long as it isn't 0 because division by 0 isn't defined, right? Okay? So, you have that. So where's the numerator 0? Well, there's 4. It's 0 at 5. It's 0 at 6. Okay, so, and at -4. So I'll just kind of put an X through this point, and this point, just to remind myself that those will be zeros. I'm going through those points. So you have to put those vertical lines in there to remind yourself of what happens as you get close to -6 and 4. And X is here. And these are the only places it can go through the x-axis. If it passes through the x-axis, it's a 0. Okay? The only way it's a 0 is if this numerator is 0 and the denominator isn't. So we want to understand those statements so you can put them together. Now you work out the pluses and the minuses. We've done that many times, so I'm just going to write them down. I'll explain it as I go, but I'm not going to write down the reasoning. If x is a negative, big negative number, past -6, if x is less than -6, then every one of these expressions is negative, right? Now, you've got this expression twice, because this really means x minus 5 times x minus 5, right? So you got 2 negatives there. And here's a third one, and here are 3 more. You got x minus 6, x minus 6, and x minus 6, right? And that seems to add up to 6 negative numbers here, right? And then you have 3 down here, right? Okay? And you can write that as negative, 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 divided by negative, negative, negative equals negative. Okay? Now between -6 and -4, you could pick x equals -5. Okay? And determine whether this is positive or negative when x equals -5. Okay? So you can actually plug in -5 into each one of these. You'll get a positive or negative on each one. And then you can figure out what you've got, right? Okay? The thing I wouldn't do is use a distributive law and multiply all these out. Of course, if you multiply them all out, you're going to use a distributive law, okay? It's going to be a mess. And I wouldn't multiply these out and then plug in -5 to what you get when you multiply them all out. I've seen people doing that. That's good because your distributive law looks really good and you seem to be doing everything right. But it's much easier to plug in -5 here, 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 and here, and here. You're going to get -10, you're going to get -1, you're going to get -11, you're going to get 1, you're going to get -9. Now you can multiply those numbers together and then divide by them. Okay? But you don't even need to do that. All you got to do is know that, okay, if x is -5, that's negative. That's obviously negative, right? You can calculate it if you want, it's -10, but you don't have to do any more than that. You just have to know this is negative. So that gives you, two negatives. This is negative. It gives you another negative. This is negative. That gives you 3 more negatives. Divided by this, well, x plus 6 is going to be positive, but x minus 4 is going to be negative. So we're going to have 2 positives and a negative. Okay? Does that make any sense at all? Now, if you got to put in -5, it's not that hard. You just write down the numbers and then look at them, and you'll know whether it's positive or negative because you just count up your negatives. How many do you have, right? And you can tell that the function has to be negative. Well, you do the same thing between -4 and 4. What's the easiest number between -4 and 4 that you can plug in? Well, it's kind of automatic. You always want to find the y-intercept. Y-intercept occurs when x equals 0, and the y-intercept happens to occur then x equals 0 happens to occur in the interval from -4 to 4. So you can see that if x is 0, you got 2 negatives here, right? And you got a positive, and then you got 3 negatives. So you got 2 negatives, you got a positive, and you got 3 negatives in the numerator. And down here, you've got 2 positives and a negative in the denominator. So you've got 5 negatives up here, 1 negative in the denominator leaves you 6 negatives, which is positive. So it's positive. So the graph's going to be above the axis here. It's going to be below the axis here and here. Okay, well, between 4 and 5, take 4.5. That's going to be negative, that's going to be positive. So yes, that's negative, so you got 2 negatives. You got a positive, you got 3 negatives. You have a positive here and a positive here. That's 5 negatives. So you're negative in this interval. Between 5 and 6, if you got 5.5, you don't actually have to calculate it. You just know if you got 5.5, well, 5.5 minus 5 is a half. That's positive, right? So you got a positive times a positive here. So I'm going to write it down here so as not to confuse it anymore than it already is. 5.5 here makes it positive. Now you got 3 negatives because of the 6. 5.5 minus 6 is negative. All you got to do is compare. You don't have to calculate it. The only one you really want to calculate is the y-intercept, because that kind of gives you a scale to the y-axis. Okay, and then x is 5.5 here. This is going to be positive. That's 2 of them, and another positive. You got 3 negatives. Okay, which means it'll be negative in this interval. On this interval, everything is positive. So you're going to have three positives, 3 negatives. So that's positive. Okay? That's how you reason it out. You don't have to do a lot of heavy calculation. You just got to look at each factor and see what you've got. Okay? Now, I'm going to write down a principle there. So I'm saying to figure positive or negative on an interval, you look at whether each factor is positive or negative, counting multiplicity. What I mean by multiplicity? It means how many times this thing actually occurs, right? You got to count that twice. You got to count this 3 times. You got to count this twice. Okay? Then we want to look at far right and far left. Okay? So, end behavior consider large positive and large negative x values. If x is a huge positive or a large positive number, you know, a lot bigger than 6, because large starts a lot bigger than your rightmost 0 or asymptote, right? Or large negative starts at your leftmost 0 or asymptote, okay? And goes quite a ways further. So if x is a lot bigger than 6, then every one of these is positive. Okay? Also, you got 6 of them in your numerator and only 3 in your denominator. So you've got 6 big numbers in the numerator, you get a 6th power of a large number, basically, okay? If you've got 3 of them in your denominator, that gives you a 3rd power of a large number. And a 6th power divided by 3rd power gives you a 3rd power, which is going to be a humongous positive number. So in this case, you approach a humongous positive, and if you figure it out for negative, well, you're going to have, ultimately, you're going to be left with 3 humongous negatives. Okay? So now, how do you construct the graph? You might even want to then draw the thing with just the negatives, the positives, the negatives, and the positives, and the asymptotes and the zeros, so you can construct it without having to go through everything else you've labeled, but you can do it here. So we got to stay negative over here, but we got to start from way down, and we got to have an asymptote here, right? Well, the asymptote has to be a negative asymptote because the thing is negative all the way on the left of this. It's always got to be negative. So we're going to have something that kind of does this. It's the only way it can happen. Okay? And then here, we're still negative. We've got an asymptote, so it's got to be negative here. But it's got to go through 0 here and then become positive, right? There's the story. If you figured it all out, you know, then you've got to do this. Now you can kind of anticipate that you're going to also have a positive asymptote when you get over here. So you come up here, you go through here, maybe level off for a while, but then you approach a positive asymptote. So it's got to do this. Okay. Also, you might want to put your y-intercept in if you want to calculate that. What do you got? That's going to be a big number. Negative 25, positive 2,500, 21,600, negative 21,600 here, divided by 36 times 4, which is 144. 21,000 divided by 100 is about 2. Okay. I'm going to say it's maybe 100 and something. So you might put that on your x-axis, okay? Maybe your x-intercept here, or I'm sorry, your y-intercept is, I'm guessing, around 150. Giving you an idea of the scale. It gets pretty big here, but then it gets humongous over here. Okay? So it doesn't hurt to do that. Over here, you're going to have a negative on the asymptote. It's going to have to come up through 0 here, except it can't go through 0 because then it would be positive over here, right? Okay? It comes up from here. It's going to have to turn back around into the negatives. And then it's going to have to turn around again to come back to this 0. And then it's going to just take off. Okay? So I'm thinking it's going to come up through here. It's got to have a 0 here. And it just takes off. Okay? And you can't make it go through 0 someplace else to do what you think it ought to do. If you think it ought to go through 0 someplace else, you're thinking wrong. Now, let's see how this works out. Okay? The graph isn't totally accurate, okay? Because I just went through 0 here without looking at the fact that this behaves, this 0 comes from the x minus 6. Okay? So really what I should have done here is when I come up here, I go down here, I come up here, and I level off here before I take off. That's like an x cubed function there, isn't it? That's the way an x cubed function behaves. Near x equals 6, this is just a horizontally translated x cubed function. Now it's also stretched by whatever all this is. Okay? So it's a vertically stretched and horizontally translated x cubed function. That's an important idea. Okay? Now if you get everything else and don't get that, and how the power of this thing gives you the shape, well, it's still not bad. Certainly ain't A work. Okay, more like high C, low B work. But that's not bad. So you try to get that multiplicity because you get a lot more credit if you understand it. If you understand how this is a translation and all that stuff, you get a much better picture. You're showing much better grasp of what graphs can tell you. Okay? But if you do all this and don't quite get that multiplicity, it's probably still 7 or 8 out of 10 if you get everything else right. Okay? Maybe even better depending on how I'm grading. It would be more than 8. Okay? Okay. Notice that x minus 5 squared, you can say the same thing. Near x equals 5, this has to behave much like a vertically stretched and shifted x squared function. And you see it right there. It has to look like that. Okay? You can't really draw it without making it look like a parabola there. Okay? It might be a somewhat distorted parabola, and it would be somewhat distorted, but I'm not going to be picky about that. Okay? What about this one? Why do you have asymptotes on the same side of the axis? Well, this comes from what? It comes from the x plus 6 in the denominator. Okay? And 1 over x plus 6 squared, or vertically stretched 1 over x plus 6 squared, would be like your 1 over x squared function, right? Vertically stretched by whatever all the rest of this tells you it has to be. Well, this tells you all the rest of it's negative, but it's vertically stretched, so it's now negative, and it's horizontally shifted over to -6. Because when you replace 1 over x squared by 1 over x plus 6 squared, that shifts you horizontally 6 units in the negative direction. So if you understand translations, you can understand why all this happens. Okay? And this is totally consistent with the graph of a 1 over x squared function. It looks just like it, except of course for the negative. You understand that. Okay? Okay, so that's kind of a complete picture of how you do a rational function. Okay? So, try to get as much of that in there as possible.